going live. And now I'm live. Yes, for those people who are in the chat right now. Excellent. I really like doing Google Meets. Last Friday, I was unable. You probably saw the video. I hope you did at least. Maybe it had like 30 something views. But last Friday, I was unable to do the live stream because my principal would not let me do the live stream. I was out sick, and he said, "No, you cannot do this from home." And I'm like, "Fine, great." It's the world we're living in now, where I can't do that kind of stuff. So I had to do most of my work in the morning, get that uploaded for you guys, and then we kind of moved on from there. I tell you, my son got tested for COVID. I did? Oh, that's right. Yes, because he got tested last Monday. Yes. So he missed 3 days of school. He came back negative, just for the sake of I'm not gonna drag that out. He tested negative, thankfully. But he missed 3 days of school. And then it was like Wednesday night, and we're like, should we send him to school? And we're like, I don't know, the tests are not back yet. The test didn't come back till Thursday morning. So Thursday morning, I had him signed into his classroom's live stream, his first grade classroom's live stream, and he's sitting there and he's doing all this stuff. And then the doctor finally calls, because I was out sick on Thursday. The doctor finally calls and says, his test came back negative. So I look at my son, and I'm just like, hey, you want to go to school? And he's like, yeah. And I'm like, oh, this kid wanted to be in the classroom. He wanted to be with his friends. I mean, yeah, they're all distanced from each other. They're all masked up and everything. But like, there's a huge difference for some kids being within a physical proximity with another student versus just being on the computer away from everyone else. Because I know kids who are like, no, put me on the computer. I hate people. No, maybe not hate people, but they kind of prefer, let me do my own thing. Let me work from home and I'll get it done. But then there are other kids that are like, no, I need to see human beings. Anyway, here's what I want to do first. I want to introduce what we're going to do with a video. I have a brief video to show you in regards to what we're going to be focusing on today. Now, I'm not going to be showing the entire video. I'm going to be skipping past some of the parts that I found a little bit boring. But the parts that I am going to show you are the parts that I deem the most important. So I am going to ask you to focus on what I'm about to show you here. Let me just click and duplicate, click. There it is. Now, this, the guy who does this video, it's a silly cartoon. Please forgive the silliness of the cartoon. I did not make it. But there are certain parts of this video that are very important. And like I said, I'm going to skip over other parts that I deem to be less important. Here we go.
Hello, I'm Professor von Schmohawk, and welcome to YU. So far, we have introduced quadratic functions and have seen that the graph of a quadratic function in a single variable is a parabola. If we set a quadratic function equal to 0, we produce a quadratic equation. Although quadratic functions and quadratic equations look similar, there are some important differences. For example, let's take the quadratic function x squared minus 4. Like all quadratic functions, the graph of this function is a parabola. Now, if we set this function equal to 0, we produce a quadratic equation. This equation has two solutions, x equals 2 and x equals negative 2. So although the graph of the function x squared minus 4 is a parabola, the solutions to the quadratic equation are the 2 points where the parabola intersects the x-axis, also known as its x-intercepts. These points are called the zeros of the function. In general, the zeros of a function are the input values that cause the function's output to have a value of 0. So for a function of x, the values of x which cause the function to produce a value of 0 are the zeros of the function. These zeros are sometimes called the roots of the function. Finding the zeros of a linear function is easy, since unless the function's graph is a horizontal line, it will always have a single x-intercept and thus a single zero. To find the zero of a linear function, we determine its x-intercept by setting the function equal to 0 and then solving the equation for x. On the other hand, a quadratic function of a real variable may have two x-intercepts, one x-intercept, or no x-intercepts. But solving a quadratic equation can be much more complicated than solving a linear equation. The problem of finding the solution to simple quadratic equations was encountered at least 4
I'm going to skip this part because this part's dumb. I don't like this part. There we go. That's the part I wanted to get back to.
The trajectory of a free-falling object can be described by a quadratic equation. As an example, if a cannonball is fired from a cannon 12 meters above the ground, and the cannonball has an initial vertical velocity of 80 meters per second, then according to the laws of Newtonian mechanics, the height of the cannonball above the ground would be given by the function -5t squared plus 80t plus 12, where the constants in this quadratic expression are determined by the physical parameters of the example, and t is the time elapsed after the cannon is fired. If we wish to find the time it takes for the cannonball to hit the ground, we set this expression for the vertical height equal to 0, and solve the resulting quadratic equation for t. Solving this equation requires a mathematical technique more powerful than anything that the Babylonians or Egyptians had in their mathematical bag of tricks. In the next several lectures...
I'm not going to... Because he's going to talk about the next several lectures. I don't care about that. What I care about is this. Today, we are going to be solving quadratics. Today, we are going to be focusing on solving quadratics by factoring. Last week, I focused a bit on the Tucker method of factoring. In fact, that quizzes that you have due for me today at 2 o'clock is based on the Tucker method of factoring. Actually, not the Tucker method of factoring, just factoring in general, but you could use the Tucker method if you want. Today, we're going to be focusing on solving these equations by factoring. But this equation right here cannot be solved by factoring. It cannot be solved by factoring. Oh, but it can be solved. Real quick side note. In Algebra 1, did you guys learn a really messed up formula that you wished you had never seen before in your life? Most likely. Negative b plus or minus squared, b squared minus 4ac all over 2a. I don't know if your teacher had you memorize something like this. I don't know, I'm just saying, yeah, but that's the formula. This formula we're not learning today, but this formula is eventually the end goal. See, there are two main ways to solving quadratics. Number one, factoring, which is what we're going to be focusing on today. The other main way is the quadratic formula, which is something that has to be used if factoring is not available to you. And we're going to get into those details. Now, I don't know how many of you are familiar with Desmos. Desmos.com, wonderful website. Let's log in. Use the graphing calculator. And let me put in a function like this. There we go. Now, this function, x squared plus x minus 6, should look very familiar. I gave you that equation last week when we first started about factoring. It's one of the first equations that I gave you in regards to showing you how the Tucker method works. And eventually it came back again in one of the examples that I gave you later on. There are 2 points on this graph that we are focused on today. Oh, my marker. Sad days. There are 2 points that I'm focused on. From the video, they talked about where it hit the x-axis. And this is where, if I can get this marker to open one-handed, yes. And this is where our focus is going to be on today. Now, honestly, if you saw the graph, you can visually see what the answers are. Mr. Markey, clearly, one of them is a -3 and one of them is a +2. Yes, good. Happy day. You did it. They're not always going to be that easy. They are not always going to be that easy. And when they are not that easy, you are going to have to show me some mathematical work to back it up. And that mathematical work would either be by factoring or the quad formula eventually. But this is what we're going to be solving today. They showed the cannonball firing off the top of the tower, which I thought was really interesting. It's like, I don't know how many armies use cannons nowadays. I mean, I don't really know that many. But back in the day, when you had a cannon and you had 2 armies coming at each other, you may have something like this where there's like a cannon being fired. I don't want to draw a cannon. And it's being fired in this direction. And there's all these troops down here that are rushing up the hill, and they're like, we're going to get them. Just imagine these are great troops, and they're rushing up the hill. And the idea is like, well, we have to defend ourselves, so we have to fire the cannon. But you have to fire the cannon. We know what the muzzle velocity is. We know what angle we're going to fire this thing at, but when do we fire it? And the idea is that whenever that thing was fired, the path that the cannon would follow would be a parabola. And if we knew precisely when that cannonball would hit the ground and how long it took to get there and how long the troops were coming in the other direction, if you were mathematically astute, you could blow those people up. It's insane. You ever watch the movie Glory? You have? Well, when I was in 8th grade, we watched the movie Glory in class. And my teacher, who was a bit distracted by fun things, we watched the movie Glory, and then he paused it. And he's like, did you see? Did you see? And I'm like, see what? We just saw somebody's head blow up, literally, in the movie. There's like a scene of a guy's head blowing up because of a cannonball hitting him precisely. And he's like, did you see? Did you see? And I'm like, what? And then he rewound it, and we watched it again. And we're like, yeah, the dude's head blow up. He's like, no. Did you see what color his eyes were? Did you see what color his eyes were? And we're like, no, what are you talking about? This is my 8th grade social studies teacher telling us this. Did you see what color his eyes were? And we're like, no. So we watched it again. And he's like, they were blue. One blew that way and one blew that way. There you go. Anyway, ladies and gentlemen, here's what I need from you. I'm going to need those notebooks out and open. You too, in the chat, you people that I'm looking at now, take out them notebooks. I had the weirdest 8th grade social studies teacher of all time. Fun fact, my 8th grade social studies teacher is now currently the Barnegat athletic director. Not kidding. Correct. Now the story makes a lot more sense. Oh, fun times. I don't think he remembers me at all, by the way. I've worked with him for 12 years. I don't think he knows any. He doesn't even know who I am. You know? All right. Solving quadratics by factoring. Today is the 22nd. Solving quadratics by factoring is the bread and butter of Algebra 2. It is the bread and butter of Algebra 2. It is something that they tried to teach you in Algebra 1, and maybe it stuck, maybe it didn't. I don't know. But solving these quadratics, finding out where they cross the x-axis, that is one of the most important skills that you are going to have. Because solving quadratics is in this chapter, which is actually technically chapter 4 in the textbook. It is also chapter 5. There's also a little bit in chapter 6. There's also a little bit in chapter 8. Solving by factoring is one of the most important skills that you are going to learn this school year, besides keeping your masks up. Now, let's start with something like this. Solve x squared plus x minus 6 equals 0. Now, I know what the answers are. Clearly, we know what the answers are. We saw them. We saw the answers on the graph earlier. Let me flip my screen back, actually. If I flip the screen back, you can see it right there. Where does that graph cross the x-axis? It crosses the x-axis at positive 2 and at negative 3. They work, positive 2 and negative 3. Let's just confirm that. I can literally just plug something in like this, positive 2. By the way, what I'm writing in red, you don't have to write because I'm going to erase it in a minute. But if I plugged in a positive 2, you can see, yes, indeed, it works. 2 squared is 4. 4 plus 2 is 6. 6 minus 6 is 0. Yes, it works. Fantastic. Let's try negative 3. Negative 3 squared is positive 9. Positive 9 plus negative 3 is 6. 6 minus 6 is 0. Yes, they work. They are the answers. But, once again, they're not always going to be that easy. They're not always going to be that straightforward. They're not always going to be a number that you can guess. They're not always going to be a number that you can see. We're going to have to solve this thing. And, again, I mentioned by factoring because that is the name of the game. So, we need to begin this process by factoring. Yes? Yes, give me, here. If you can fill this out for me real quick. I'm just going to continue with the next couple of things. So, the name, date, time, all that other stuff. So, I need to start with a GCF. However, the GCF of this particular problem is 1, so that doesn't really help me at all. So I skip the GCF, and I move on to step 2, which is A times C. A times C gets me negative 6. Again, this is one of those problems that we did last week. I have to find 2 magic numbers. Do you guys remember what the magic numbers were for this particular problem? 2 numbers that multiply, C205, that multiply to give you negative 6 and add up to the B value, which, by the way, the B value for this problem is a 1. Yeah. 3 and negative 6. Yeah, we did this last week. We did this like twice last week, right? That's like the 3rd time we've seen this. 3 and negative 2. I'm trying to remind you of the Tucker method. I'm trying to remind you as to what it does. So we did a little T-chart. We put those magic numbers in the bottom of the T-chart. It was an x squared, so we put a 1x and a 1x. Nothing simplified, which got us x plus 3, x minus 2. But now we have this added thing of an equals 0, which is good. By the way, you ever look at equals 0 and turn your head to the left? Left. There you go. He turned it the other direction. Doesn't it look like a face? Yeah. I have no real reason to bring that up. I just thought it was funny. Anyway, these terms right here, these terms, they are not my answer. They are not my answer. These are factors, not the answer. These are factors. These are not my answer. The Tucker method gets you to the point of factors, where you have two factors, or three or four, however many factors there are. But the Tucker method gets you down to the point where you can break these things apart into multiple pieces. It's still equal to 0. We still don't have our answer. We're still not there quite yet. But I just wanted to point out that that concludes the Tucker method, but it is not the answer to the problem. The answer to the problem is a bit more complex, and we're going to get there. So, I got to give you a little bit of a background piece of information on this. Move that up. There we go. To solve a quadratic means to find the x-intercepts. As the video talked about, they're trying to find x-intercepts. But they said other names in the video. I don't know if you remembered what those other names were. They called the x-intercepts by another name. There were actually 3 other names that they called them. Anyone know them? I know the video, silly video with a guy with a British accent. I wish I had a British accent. No, I said I wish. I said I wish. I know. I've been watching a lot of DuckTales lately, so I got like a Scottish accent in my head. You guys ever watch DuckTales? It's so good. Just saying. I grew up with the original DuckTales. Shut up. Anyway, the other one that you go with, the other name that you could call them, they also refer to them as roots. They also refer to them as solutions. They also refer to them as zeros. All four of these terms, they mean the same thing. They all mean the same thing. If they say, hey, find the zeros of the quadratic, or identify the x-intercepts of the quadratic, or find the roots of the quadratic, or solve, finding the solutions of the quadratic, they're all asking you to do the same thing. They're all just calling it by a different name. Why do they have so many names? I don't know. They just do. Over the years, that's just what they've ended up calling them. But they all mean the same thing. If they say solve, or find the roots, or identify the zeros, they're all asking for the x-intercepts. They're all asking, where does it cross the x-axis? That's what they want to know. That is exactly what they want to know. So, moving this aside. There we go. To solve a quadratic, I said to find the x-intercepts, yes, but I'm going to write something else here. To solve a quadratic means to let y equal 0. To solve a quadratic means to let y equal 0. I'm going to draw this on the board real quick, just so we can all kind of see this. Which one is the x-axis? You can kind of mime it with your hand. Yeah, we did it. Woo! Anyway, this is the x-axis. This is the y-axis. Now, I want to find an x-intercept. An x-intercept, meaning, I don't know, maybe that's my x-intercept right there. If this is my x-intercept, kind of gave that away, whatever. It's some kind of a number for my x-intercept. I don't know what number that is. But if I am on my x-axis, if I am hitting an x-intercept, what is the value of y? If I am on the x-axis, what is the y value of the ordered pair? It's 0. Yeah. It's 0. On the y-axis, I am right at 0. To solve a quadratic means to let y equal 0. This is very important for understanding this process. If you are going to begin solving a quadratic, you have to have the y value equal to 0. Now, initially, for this problem, you might have a quadratic like this, where it's y equals x squared plus x minus 6. But now, because of solving a quadratic, we have to let it be 0 equals x squared plus x minus 6. By letting the y value equal 0, we are taking the next step towards solving that quadratic. What has been like the overarching goal of mathematics since like day one when cavemen walked out of their caves? Do you know what the goal of mathematics has been since you started school all the way back in kindergarten? Solve for x. That's literally been it the entire time. Solve for x. Isolate x. Get x by itself. Hasn't that been the goal? Maybe not since kindergarten, but like since like maybe 5th grade, something like that. I don't know. The goal has been to solve for x. Figure out what x is. X equals. So now what we have done is we have taken this quadratic and we have factored it into these two terms. I'm trying to walk you through literally everything that mankind has done from the cavemen to today. And once I walk you through this process, you're going to understand. You're going to understand what the heck we have to do next. I have a side note for you. And this is literally a side note. Like I'm literally writing the word side note. If I have two things multiplied together, and the result of that multiplication is 0, what do you know about those two things? Let me repeat the question. Real quick. If I multiply two things together, and the result is 0, what do you know about those two original things? Yeah, one of them has to be 0. Could they both be 0? Yes, of course they could both be 0. But at the very core level, one of them absolutely has to be 0. If a times b is equal to 0, hey, looky here. X plus 3 times x minus 2. A times b. Two things being multiplied together, and the result is 0. This is called the zero product property. The zero product property is what this is called. If you have two things being multiplied together to give you 0, one of them has to be 0. Now, they both could be 0, but we just don't know which one. Oh, it's then either A equals 0 or B equals 0. It's a pretty sweet pencil sharpener. I had an old pencil sharpener that like broke literally the first month I had it in the classroom, and we used that broken pencil sharpener because I devised a way to like get a piece of plastic stuck up into the gears to make it work. And we used that broken pencil sharpener for like 5 years until finally I bought that one. Whatever. Either A equals 0 or B equals 0, which means based on what we had on this previous page, based on this zero product property, it allows us to make the following step. Either x plus 3 equals 0 or x minus 2 equals 0. That is what this step allows us to do. If we can take a quadratic and we can break it apart into its factors, and this whole thing is equal to 0, then we are allowed to take the factors and separate them and set them both equal to 0 and then solve. And we get the two answers that we were looking for. We get the answer of -3, and we get the answer of +2, both of which are our answers. There are two answers. There are two solutions. There are two roots. There are two x-intercepts. There are two zeros of the function. They could be called all those things. It's wonderful. Let me come up with an example. I want to come up with something here. Let me think of something that could work. Give me a single digit number. 4. Okay, hold on. That could work. Okay, here we go. I'm trying to come up with an example off the top of my head, but I need it to work. So we're going to solve 2x squared. Can I get that to work? Yeah, I'm going to get it to work. Plus 9x plus 4 equals 0. That absolutely works. I put the 4 at the end, but it works. They don't work all the time, ladies and gentlemen, but this one absolutely does work. Let me jump to Desmos. 2x squared plus 9x plus 4. There we go. There is the equation, and there is the graph. And it looks wonderful, ladies and gentlemen. It looks so wonderful. Clearly, you can visibly see two x-intercepts, which means that this problem has two solutions. It has two zeros. It has two roots. You could probably guess what that number is. It looks like -4. What the heck is that number? It's not a whole number. It looks like it, right? Is it though? I mean, it might be. It might be. Hold on. Let me kind of zoom in a little bit. Oh yeah, look at that. You know what Desmos does for you? Click. Look at that. Zooming in, zooming in, zooming in. -0.5. But you don't always have Desmos. And you don't always have nice answers. And I always need to see the work. Well, not always, but whatever. Click. Let's see what we can do here. Based on everything that we've done, we need to go through the Tucker method of factoring. So, greatest common factor. Step 1 is greatest common factor. Oh, look, a 2 and a 4. Don't they have a 2 in common? Yeah, but the 9. Crap. Yeah, I can't do that then. So I move on to step 2. A times C gives me an 8, +8, because 2 times 4. Give me two magic numbers. Two magic numbers that multiply to 8 and add up to 9. 8 and 1, I know. People forget the 1 sometimes, but 8 and 1. 8 and 1 totally work because they multiply to 8 and add up to 9. Cool. T-chart, 8 and 1. Anyone remember what the heck I put in the top of the T-chart? Because before it was a 1x and a 1x, but what do I do here? It's from last week. What dost I do? I got to do 2x and 2x. 2x and 2x. Nice. I got to simplify. In the T-chart, you put the magic numbers in the bottom, but you, in this case, 2x and 2x because of the 2 in front of the x squared. But I got to simplify. 2 over 8 reduces to 1 over 4. 2 over 1, I'm going to leave it as is because I can't reduce that. 2 over 1 would stay 2 over 1. I mean, Ms. Murray, it's a 2. I know, but the 1's got to stay on the bottom, which means this becomes x plus 4 vertically and 2x plus 1 vertically equal to 0. Now that concludes the Tucker method. This is not my answer. These are not my solutions. These are simply factors. These are the factors based on the Tucker method of factoring. The Tucker method is done at that point. But now we have to rely on the zero product property. The zero product property allows me to do this. This only works if you have it equal to 0. This only works if you have it equal to 0. And now this goes back to, I don't even know, when did you first guys learn junk like this? 6th grade, maybe? I don't know, kindergarten? I don't know how ages work. I mean, my kid's doing calculus right now. How are you guys doing? No? No, my kid's not doing calculus. You kidding me? Kid's 6 years old. He's playing Mario Odyssey, though. Anyway. I get an answer of -4. And here, I got to subtract 1. I got to divide by 2. And yes, I get -0.5. It's exactly what we believed it was. It's exactly what we thought it was based on the way the graph looked. Chapow. Looking at that graph, it looks like -4. It looks like -0.5. We proved it. We proved it using the Tucker method of factoring and the zero product property. That is what this thing does. Quick math?
Yeah.
I don't get it.
I said math.
Maths?
Yeah.
Maths?
No, math.
Math?
Yeah.
Math? So confused. All right, it's time for my nap. You know, when I was sick last week, I legitimately, accidentally took multiple naps. Yeah, I, passed out on the couch for, an hour. It was glorious. In the middle of the day, it'd be, 11 o'clock in the morning, and I'd, just pass out. But, of course, I was sick. All right, you ready for this? Don't panic. Wait for the shiver. I got a word problem for you. Let's say that you are building some kind of rectangular device, whatever that rectangular device is. And you are told that the length and the width have to be 6 feet apart. The length and the width have to be 6 feet apart. And the area that you are given to work with is 16 feet squared. This is all the information they give you. You are building a rectangular device of some sort on the ground. And they say that, the width has to be 6 feet longer than the length. Okay. But the area that they've given you to work with is 16 feet squared, or 16 square feet. Something along those lines. It's almost like something similar to this, maybe what the project is about next week. That's a hint. I don't know. So my question becomes, okay, what is the value of X? What is the length of this whole object? I guarantee you can figure this out just by looking at it. I guarantee you can. Just by looking at this, you can figure out exactly what the value of X is supposed to be. Now, that's not the point. I still have to have the work to back it up, the algebra work, not the plug and chug. But just for the sake of argument, what value should X be in order for this object to work? How do you find the area of a rectangle? I can hear crickets. Come on, geometry fans. How do you find the area of a rectangle? I gotcha. But you're about to say length times width. You're about to say length times width. length times width should be equal to the total area, which in this case is 16 feet squared. If that is the case, length times width, what should the value of x be in order to make this true? It's a whole number. It's a nice number. It's a positive number. Oh, no one wants to say it. Oh, I think at this point you guys are too scared because it's gone on too long. You ever have that moment where like nobody answers and then it's still like, man, too much time has gone by, and if I answer now, it'd be really awkward. You know what I'm saying? Yeah. So, what number comes after 1? Say 2. No, just say 2. No one can hear me right now. Yeah, we did it. Oh, goodness gracious. Anyway, back to this. Clearly, you could figure this out just by looking at it, but I need to see the algebra to back it up. So, based on what you told me about length times width, length times width is equal to the area of this object. This is a word problem that we're doing. I mean, you don't really see a lot of words, but I'm still backing that up. So I got to solve this junk. I got to solve this junk. I'm telling you, this is going to be a quadratic. I don't see a quadratic. So I do have to simplify this a little bit. I have to do this ancient method starting with a D and ending with an distribution. No one wants to say it. It's turning into one of those classes, isn't it? Where people are just like, nope, not saying it, not changing the culture. You got to distribute. In this case, x times x would get you x squared. 6 times x would get you 6x. And we are equal to 16. Now, hold on a second. Because this is probably the most important thing that you have to recognize during this lesson today. What I'm about to teach you now is one of the more important things that you have to recognize during the lesson today. We have this quadratic up here. We have x squared plus 6x equals 16. And yes, I would love to begin with the Tucker method of factoring, and then I would love to solve that thing out to get my answers and to finally answer this math problem. But I'm faced with a little bit of a dilemma. The first problem we did today was this. The second problem we did today was this. The third problem we're doing today is this word problem that I have on the board. There's something wrong with the problem on the board. There's something wrong with the word problem. There's something that we have to do in order to fix this problem, in order to proceed, in order to move forward, in order to get to the Tucker method. I have to do one more thing. What is it? What do we have to do? What is the big visual difference between problem 1, problem 2, and the problem we're currently on? You have to get it equal to 0. You have to. That is one of the biggest requirements in this entire thing. And I'm spending a lot of time on this moment. I'm spending a lot of time reiterating this point so that you have this memory, this light bulb, this flash bulb memory in your head to remember that if you are going to start solving a quadratic, if you are going to start using the Tucker method, you have to have one side equal to 0. If you do not have that one side equal to 0, then it is not going to work. I've been building up to this moment the entire class period. Y has to equal 0. They're called zeros of the function, things of that nature. This is what we have to solve. It just said subtract 16. So now you have the quadratic equal to 0. Now I'm actually going to bypass one step. I'm going to bypass one step. Let's pretend that I did the Tucker method. Let's just pretend that I did. I would end up with x plus 8 and x minus 2 equals 0. These are the two terms that I would end up with. Again, bypassing the Tucker method. Hopefully you can visibly see, oh yeah, 8 times negative 2 is negative 16, and 8 plus negative 2 is positive 6. Hopefully you can see that being worked into the Tucker method. So then I continue solving using the zero product property. I set each of these equal to 0 using that zero product property. And I end up with my two answers of negative 8 and positive 2. Oh, hold on one second. I got to stand back up for this. Don't circle your answer. Don't circle your answer. Don't circle your answer. I know some of you already tried. Don't circle your answer. We know the answer's 2. We know the answer's 2. First and foremost, this is a word problem. And since it is a word problem, word problems deserve units. What is the unit on that 2? Feet. Because it's 16 square feet for the area. Yes, it's got to be 2 feet for my answer there. What the heck is this? I got 2 answers. Can I also use this? Shaking your head, no. It would be like, what, negative 8 feet? That doesn't make any sense. Negative 8 feet doesn't work. See, the thing with word problems is a lot of the time you might get an answer that just doesn't make any contextual sense. If I just gave you this problem, or this problem, for example, if I just gave you this problem out of the blue, no context, no feet, no construction, no word problem, if I gave you this and said, solve that, boom, you got my answers. Oh, happy day. We'd move on from there. But it's a word problem. And if I go back to the original problem and I think about, they wanted me to solve for x, but x is the length of this rectangle. You can't have negative length on a rectangle. As a result, I'm just going to cross out that negative 8. Don't erase it. Don't erase it. It's part of your answer. You want that on your answer. You want to show that you did your due diligence. You want to show that you did indeed get both answers to the quadratic, but you showed that, oh, it's a word problem. I can't have that as one of my answers. It's wonderful. I got 2 problems for you to try. I got 2 problems for you to try. I'm going to split my page. Whee! I want you to solve x squared equals 2x plus 99. And I want you to solve 2x squared minus 8x minus 90 equals 0. These are 2 problems that I would like you to try. Now, a couple of pieces of advice. Before you continue. If you want to start solving this one, you need to get one side equal to 0. I would suggest keeping the x squared positive. Keep it positive and move everything over to the left side using subtraction. For this second problem right here, you have to remember to take out your greatest common factor. And once you do, then you can proceed with the problem. I'm going to give you guys roughly the next 5 or so minutes, maybe a little less than 5 minutes, to knock out both of these problems. You people at home, do the same thing. But let's see what we can do with these 2. Go. gave this speech to yesterday's Algebra 2 class. I'm going to give you guys the similar speech in that regards. If you heard it before, that's okay. I'm going to give it again anyway. When I was a kid, we had a stove that had a pilot light on it. Most of you guys may or may not know what a pilot light is. Nowadays, you turn on your stove, like the burner or whatever, and it goes click, 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 and then it blows up, right? Yeah. Back in the day, it didn't do that. Back in the day, there was what they called a pilot light, which it didn't have to go click, 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 light. It was like you'd turn it and it would just light. But on the top of your stove, there were these like little holes. If you looked down into the hole, you could literally see a blue flame. I was like, oh, that's kind of cool. So I was like 4 or 5 years old, and I'm sitting on the counter in the kitchen, and I look over, and I see this blue flame. And I'm thinking to myself, as a 4 to 5 year old kid, I'm like, I've never seen this before. I wonder what would happen if I put my thumb on top of that. So I reached over, and I put my thumb over the hole. What do you think happened? Yeah, probably. Burnt my thumb. 2nd degree burn on my thumb. It was pretty bad. But I learned something. And the reason why I learned something was because I was willing to put myself at risk. Now, I'm not saying you need to put yourself at risk. I'm not saying to you whatsoever. But what I'm saying is this. A lot of high school math students are afraid of getting burned. And what that means is they are afraid of trying problems on their own. Now, you guys all worked on these problems, which was fantastic. Yesterday, I had at least 2 or 3 kids in the class who were just sitting there doing nothing. And I gave them this speech. I'm like, most high school math students are afraid of getting burned. And what that means is being wrong. They're afraid of being wrong. If I don't try the problem, I can't be wrong. Now, they may not say this out loud, but they're thinking it somewhere in the subconscious of their minds. As long as you don't try it, you can't be wrong. As long as you don't try it, you can't fail. I'm telling you that in order to be a successful math student, you have to be willing to be burned. You have to be willing to be wrong. You have to be willing to be incorrect in order to be corrected and be better in the future. The only way that you be a better math student is if you're willing to put in the work, if you're willing to get your hands dirty and try the problems and put your thumb over that flame. Sometimes it'll work. Sometimes you'll walk away burned. But at the very least, you'll have learned something. That's my philosophy of teaching. When I was in college, we all had to type up this philosophy of teaching. It was this weird, stupid thing. And I used that story. And I thought it was phenomenal. I don't know. Oh, fun stuff. Back to this. You could, if you wanted to, move the x squared over, but then you'd have a negative x squared. Having a negative x squared is troublesome. Having a negative x squared makes your life a lot harder. Instead, subtract the 2x, subtract the 99 in order to get one side equal to 0. Walk through the Tucker method. A times c is negative 99. Ugh, negative 99. Oh, wait. What are 2 obvious numbers that multiply to 99? Okay.
Oh, negative 3.
But those won't work for what I need. You know why? They got to add up to negative 2. Ooh. 9 and negative 11. But that's okay, because now you're kind of like, oh, I got to remind myself to look out for that b value. That's okay, though. So now, I got 9 and negative 11. Well, the t-chart doesn't really make a difference here. But I get x plus 9, x minus 11 equals 0. Remember, those are not my answers. Those are my factors. I get an answer of negative 9 and positive 11. It works out perfectly. Check this junk out. just to kind of zoom in a little bit before we do the last problem. Check this junk out. It'll focus in a moment. It was x squared, and it was 2x plus 99. Yes. So I'm going to go negative 10. Yeah, I'll keep it negative 10 to 10. But then I'm going to go 100 to 130 on the y-axis. There's the quadratic. Where's my straight line at? Oh, I see where it's at. Okay, hold on. I got to go to 12 here. Let me go 0 to 150. There's the quadratic. Yep, there's the straight line. Got him. So what's really nice about this, I'm going to zoom back out for a moment, is that I have an x squared equal to a linear function. I have an x squared equal to a linear function. This is just kind of a little advanced thing. There's my x squared, that parabola, and there's my linear function. Look where it's blinking. You know what point that's blinking on? Not the ordered pair, but like, you know what they call that point? They call it the POI, the point of, say it? No, I'll say it. It's the point of intersection. The other one was 11. Boom, there it is, on the point of intersection. It's just so nice to see that visually, you know? But like I said, typically you could see it a lot better if you saw the basic quadratic. Oh, I got to zoom out just a little bit. Put this to 12. There we go. There's the first part of the quadratic. There's the second part of the quadratic. And there it is at negative 9, comma 0. And there it is at 11, comma 0, our two answers. There's just so many different ways of checking our answer. So many different ways. But then we come to the second problem. And I said for the second problem, ladies and gentlemen, for this second problem, you got to check that GCF. This side of the problem, listen very carefully, this side of the problem has an Egyptian king in common. They have an Egyptian king in common. And you're like, what the heck? What do all three of these numbers have in common? They have a 2 in. They have a 2 in common. An Egyptian king. Y'all heard of King Tut? His real name is Tutankhamun. It's a hilarious joke. Nobody gets me. Anyway, x squared minus 4x minus 45 once I take the 2 out. You know, if I were you, I'd be like rolling on the floor laughing right now. It's a hilarious joke. Multiple knee slappers. That equals 0 looks weird. Equals 0. There we go. Now, when you take that 2 out, that 2 is a factor. That 2 is a factor, but it doesn't play into the rest of the Tucker method. That 2 is just sitting out there all pretty, and it's going to stay there the rest of the time. So I continue with the Tucker method. Now, within the parentheses, I would do something like this. X minus 9, x plus 5. Because 9 times negative 9 times 5 gives me negative 45, and negative 9 plus 5 gives me negative 4. Those two numbers work. According to the zero product property, I would then do x minus 9 equals 0 and x plus 5 equals 0. Technically, I would have to do the same thing with the 2. But this makes no sense. This doesn't make any sense. 2 equals 0? You kidding me? The GCF doesn't play a role. I just wanted you to recognize that. Once you take out that GCF, it does not play a role into the answer at all. Instead, we get our actual two answers. Our actual two answers of positive 9 and negative 5. 2, that 2 that they had in common was the greatest common factor. It was a factor, but it was not a solution to the problem. It was not. 9 and negative 5 were. I'm going to remind you, if you haven't already taken that quizzes, you need to do that quizzes before 2 o'clock. Please make sure you're getting on top of that. You have 3 chances to get that done. I am going to be inputting scores soon, or after 2 o'clock, I should say. I am going to be assigning something a little bit later this week that's going to be due next week as well, something similar that I did on Friday. I'm hoping on Friday to actually, I will be here on Friday. As long as nothing goes wrong, I should be here on Friday to answer whatever questions you have and whatever things we can kind of go over and clarify and things of that nature. Yeah, and that should be it. I'm going to sign off on the live stream. The bell should be ringing in approximately 35 seconds. But if you do have any questions, make sure you guys are emailing me. Click. There we go.